Hello.
Hello there.
Hello, how are you?
I'm doing alright. How about you?
Doing fine. I have two exams tomorrow.
Nice.
Two tests tomorrow. I was studying for it.
Alright.
Yeah, I just finished eating. Yeah.
Nice.
It's 1 a.m. over there right
Yeah, it's
now.
who I am right now
Oh my
for
God. Did you
me.
sleep earlier or did you stay up?
I'll stay up. I
Oh,
didn't
you stayed
sleep
up?
today.
Oh, I see. I see. Yeah, yeah. Uh yeah, today I'm still gonna go over organic chemistry stuff. So no Gen Chem stuff yet or AP Chem stuff yet.
Alright,
That's
alright.
yeah, yeah. But then you can listen in,
Alright.
like learn and get
Yeah,
and
sir, sir. Yeah.
yeah, and then we could like talk after.
Yeah.
Okay. Hey Suparna. Yeah. So we're gonna go over the hydrohalogenation of conjugated diene, halogenation of conjugated diene, and diels-alder. But I didn't prepare any notes for it because I was studying for my two exams tomorrow. So what we'll do is we'll go over Levin's practice predicted product worksheet for chapter 14, select the problems that are related to those, and then walk you guys through how I approach those problems. And then once I do enough and you guys get familiar with the process, you guys try it, and then hopefully it makes sense from there. Right, so let's pull it up. Let's see. Um, let's see if I even have it. Chapter 14. Let's see. Let's see. Uh, reactions 118. Can you send me the chapter 14 predicted product practice worksheet support not on Discord? Oh
Are
shoot.
you talking to me or are you talking to her?
I'm talking to her, Sapana, but I don't think her mic is
Alright,
working.
alright.
Yeah, oh shoot. Or
Yeah, I
yeah.
got confused a bit.
Yeah, yeah, we can't hear you, Saparna.
I can't hear her to be honest. I
Yeah, yeah,
can't
yeah.
hear her.
I can't hear her too. Oh shoot. Your mic's broken.
Recording in progress.
Yeah. That's okay. Can you send me the chapter 14 predicted product worksheet from Canvas if she posted it so that we can go over the halogenation of conjugated diene and Diels-Alder reaction. Yeah. Okay. Okay. Thank you. So, what did you do today, Davi? How was your day today?
I'm doing alright right now, to be honest.
Uh-huh.
My day was alright.
Yeah. Well, when do you go back to school? Are you still in break?
What?
When do you go back to school?
I'm going to school now, to be honest.
Oh, you go to school now?
Yeah,
Oh, shoot. How many classes are you taking?
I don't really remember. I think it's like 5 classes per day, I think.
Hmm. Let's see. So far, is it easy or is it getting hard?
It's easy for now,
Hmm.
to be honest.
That's good. Hey Jane, so today, like in this office hours, we're gonna go over the halogenation of conjugated diene, and then diels-alder reaction. But I'm just gonna go do practice problems, um, and then show you guys the thought process, and then have you guys try the practice problems by yourselves based on what I showed you, and then go from there.
To be honest, it takes so long for us as general chemistry classes take so long for you.
Oh, take so long. What takes
Yeah,
so long, sir?
it's taking long to be honest, but it's fine. I'll wait.
Oh yeah, yeah. Let's see. Or if any one of you guys have the chapter 14. Oh, I got it. I got it. Practice synthesis. Oh, yeah. So this is the practice synthesis right here. Do you have the chapter 14 reactions practice, like the predicted products ones on Canvas? Like, did she post predicted product practice for chapter 14? Let's see, because this one is synthesis. Oh shoot. Yeah. Does Jane or Amrita see it on Canvas? The chapter 14 practice, if she has it. Okay, okay. There's no. Okay. So what we'll do is we'll do the Maria Jones practice on halogenation of conjugated dienes, and diels-alder. Okay. Share screen right here. Okay. Let's do conjugated dienes and then diels-alder. Okay, so the reactions of conjugated dienes are going to be hydrohalogenation, or HX, and halogenation, or X2, right? And then you're going to see temperature with these arrows as well, but for these problems here, there's no temperature because um, they're asking you to draw both the thermodynamic and kinetic product, right? So for Leibniz class, if you see a temperature of 40 degrees Celsius, that's going to be considered hot for thermodynamic product. If you see 0 degrees Celsius, that's going to be considered cold for for kinetic product, right? And then what this means is that the thermodynamic product will make the most stable double bond end product, and then the kinetic product is going to come from the most stable carbocation, or to be more accurate, the more stable intermediate, right? Because different reactions will have a different intermediate. It does not have to be a carbocation intermediate. It could be a radical intermediate. It could be um, an anion intermediate, like any intermediate. But for these reactions here, the intermediate is going to be a cation, right? So think of cation. It comes from the more stable cation, right? Okay. So when you see DCl here, that's deuterium chloride, right? Because the D is an isotope of hydrogen. So the reason why they put that is because they want you to draw out the deuterium out explicitly in the products. You can't leave it out as invisible because it's not hydrogen. You can leave hydrogen as invisible, but you can't leave deuterium as invisible, right? So let's look at the mechanism of this to find the kinetic and thermodynamic product. Okay. Right. So if you have a symmetrical conjugated diene, in this case we do, because there's a plane symmetry down here, we only have to react with a DCl once to get one resonance set, right? If this was asymmetrical, then we would have to react with two alkenes to get two different resonance sets and then choose the better resonance set that has the more stable carbocation intermediates, right? And we'll go over that in the next problem. But since this is symmetrical, we only have to worry about one, right? So let's bring in a DCl here. This is gonna react the same way as it would with a regular alkene. We want to form the more stable carbocation at the more substituted position, right? For Markovnikov rule. That means that the less subcarbon is going to grab the deuterium, kick out the chlorine. And that's going to give us this positive charge right here, which is a tertiary carbocation, right? But it's not only a tertiary carbocation, it's a tertiary allylic carbocation, because that carbon right there is on the allylic position, one carbon away from a double bond, right? So it's even more stable than the tertiary carbocation. You'll also see that a secondary allylic carbocation is more stable than a tertiary carbocation, right? This is secondary allylic because it's on the allylic carbon. This is just a tertiary carbocation. There's no allylic component to this, right? And because it could do resonance, that makes it more stable. The secondary allylic carbocation is more stable than the tertiary carbocation. Okay, so now let's draw in the resonance structure of this, which gives us that resonance structure there, where we have a primary allylic carbocation. So the text in pink is talking about the carbocation, but let's look at the double bond here, right? The double bond on the left side is a di substituted double bond. The one on the right is a tetra substituted double bond, right? So let's determine what would give us our kinetic product versus what would give us our kinetic product. So, I mean, what would give us our thermodynamic product and what would give us our kinetic product? We said earlier that our thermodynamic product would give us the more stable double bond, which is this right side here. So this is our thermodynamic product, like intermediate, right? This would lead to the thermodynamic product. The one on the left would give us our kinetic product because it comes from a more stable intermediate, right? This carbocation right here is more stable than the carbocation on the right, making this the stronger intermediate. So when we finish up the mechanism, we get that, get this, heck. Kinetic product would be looking like this. Oh, right. And we also attacked a deuterium, so we have to draw out that deuterium out explicitly, right? This deuterium, you have to draw that out. You can't leave it as invisible because that's not a hydrogen. Deuterium, chlorine's right there. Deuterium, chlorine's right here. So this is the thermodynamic product. This is the kinetic product. Yeah, that's right. So thermodynamic comes from makes the more stable alkene end product. Kinetic comes from the more stable carbocation intermediate. Right. Okay. Now let's move on to the next one. Okay, now this is an asymmetrical example where we have to react with both alkenes and choose the best resonance set, and then disregard the other resonance set, right? So we have HBr. Let's focus on the left alkene first, right? We want to form the carbocation at the tertiary position. So this carbon is going to grab the H, kick out the bromine. Let me know if the mechanism here doesn't make sense, and then I could explain it more clearly. Right. This is the tertiary carbocation. Draw out its resonance set. That. So that's one resonance set that we have, right? But since this is an asymmetrical conjugated diene, we're gonna do the same thing for the other alkene to see what resonance set we would get, right? Protonate that carbon, kick out the Br, and then get this resonance set here. Right? Secondary allylic carbocation that could do resonance with the alkene, and then we can have carbocation right there, right? Now, these are our two resonances that we're going to be comparing. This first one and the second one right here. Right. So let's analyze what the carbocation is. For the first set, we have a tertiary allylic carbocation and a primary allylic carbocation. For the second one, we have a secondary allylic carbocation, and the other one is a primary allylic carbocation. Right. The first set is more stable because it has the better carbocation intermediate, right? The primary, that's the same thing. So we could cross that out. But tertiary allylic is more stable than secondary allylic, right? So we're gonna ignore that whole resonance set right there. Now, once we chose the best resonance set, that's when we choose what's gonna be the thermodynamic product, what's gonna be the kinetic product, right? So let's analyze the double bond now. The double bond on the left structure is a mono substituted double bond. The double bond on the right structure is a tri-substituted double bond because there's three groups coming out there. And then for this one, there's only one group coming out right there. So we see that this is going to be our thermo product. This is going to be our kinetic product, right? Where, what was it? Br minus just comes in to attack to finish up the mechanism, right? So depending on what temperature you get, you only draw one of them. If you're given 40 degrees Celsius, then you only draw the thermal product. If you're given 0 degrees Celsius, then you draw the kinetic, right? But the problem here was asking you to draw both the kinetic and thermodynamic product. So the kinetic product would look like this. Br, and the thermodynamic product would look like this. Br, right? Let me check. Yeah, that's right. Okay, now let's move on to next one, C. Right, so all of this right now, what we're doing is hydrohalogenation. The next part D, is halogenation. And the mechanism is very similar, but there are some differences. And there's one key step that you guys have to watch out for. Right, but let's do C first and then move on to that D, part D. Okay, so this is an asymmetrical conjugated diene right here. We do not want to interact with the benzene ring, right? The alkenes of that benzene ring are not going to be reacted with because it's very stable. It's aromatic, right? Which is going to be chapter 15. After you guys finish chapter 14, right? But the benzene alkenes would not react because we don't want to break the aromaticity. We don't want to break the stability there. So it's just going to be these alkenes here in that conjugated system, right? And it's asymmetrical, so we have to draw both resonance sets. Let's focus on this one first. Let's see. Let's just do that. Boom, boom, boom. Now, from here, you have to choose which carbon would be more stable with the positive charge. Where would the carbocation be more stable at? Right, let's already do that. Boom. No. Do um, Okay, so if you think about the carbocation on the left carbon right here, right? This benzene ring here does not want to break its aromaticity, so it's less willing to donate its electrons and do resonance, right? But if you think about the carbocation on this carbon right here, this alkene right here is not aromatic, it's not part of a benzene ring, so it's more willing to donate electrons and do resonance. So the carbocation on the right carbon would be more stable than the carbocation on the left one, right? Because this benzene ring here wants to keep its aromaticity. It doesn't want to donate as much, right? So let's do it like that. Attack that H, put the Cl, and that's gonna give us this intermediate positive charge resonance. So this is the first resonance set that I'm drawing here. Okay. Let's draw in the second resonance set, where this attacks that, takes out that to get us this. Right. Then draw its resonance structure. Boom, boom. Boom, 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 boom. Okay, now we get our two resonance sets that we're gonna compare. Right. This is secondary allylic. This is primary allylic. This is secondary allylic carbocation. Right. This is secondary allylic carbocation. Right. We see that the second set wins because this one ties, but the secondary allylic carbocation is better than the primary allylic carbocation. So we're gonna ignore that whole resonance set entirely. Yeah. Is problem set number 20 diels-alder reaction? I think yeah, I'll do that after I finish up these other three reactions with halogenation. Right. Uh-huh. Yeah. And then you guys could practice the other ones, and then we'll go over diels-alder after this. Okay. So now let's look at the double bond here. The double bond on the left structure is di-substituted and benzylic, right? It's able to do resonance with the benzene ring, even though this benzene is not willing to do resonance because it's aromatic. It's still possible to do resonance, right? Whereas the right alkene is just di-substituted that cannot do resonance. Like imagine if there's a what was it, chlorine right here. That's an sp3 roadblock right there. sp3 roadblock blocking resonance between that alkene and benzene ring, right? So to finish up the mechanism and get our products, this is our arrows here. Boom, boom. And then we could get that, that, chlorine. Chlorine, right? Okay, so this carbocation right here is allylic and benzylic. It's right in between an alkene and a benzene, right? So it can do resonance in both areas. So that would be our kinetic product. Whereas the double bond right here is in between the is benzylic and between the carbocation. That's the more stable intermediate, making this the thermodynamic product, right? And we have to like see what like Leeuwen's way as well, because I remember this problem helix and Nasiri disagrees with what the answer is, what's thermodynamic and kinetic. So that's why I asked if Levians had practice problems on this, so then we could follow with her rules. But this should be thermodynamic because the alkene here is able to do resonance, whereas the alkene on the right side cannot do resonance. Right. This is the kinetic product because the intermediate here is more stable. That carbocation can do resonance with the alkene here and the benzene ring. Right? It's right in between the middle, like directly. Okay. Synthesis. Okay. Yeah. So let's finish up these three problems and then do diels-alder first, and then finish up with the problem 20 on the problem set. Okay. Let's do D. Well, actually, let's do F first. F is easier, and then we'll go on to D because F is symmetrical. And if it's symmetrical, then we only have to worry about one alkene. We don't have to worry about two resonance sets, right? So the first step of the mechanism is the same as a reaction between an alkene and X2. We're going to form a bromonium ion. Right? And that's going to be this here. Right. Okay, now here's the step that you have to watch out for. Usually in the alkene chapter, you're used to attacking the more subside and then kicking out the bromine right away to get the products, right? Or if you have water or alcohol, it attacks the more subside, breaking the bromonium ion open. But in a conjugated system right here, this is a very good leaving group right here, right? Because when we kick it open, we can form a secondary allylic carbocation. So think of this as SN1 like now. SN1 like mechanism. Right? Where this good leaving group here is just going to leave by itself first. Right? The bromonium ion intermediate is going to just break off by itself to form the secondary allylic carbocation. Right? Yeah, and if there's time we can go over the NCS or NBS reaction, the allylic halogenation, allylic bromination or allylic fluorination, if you have NBS or NCS. Right. So that would be that. This would be that bromine positive charge here. And now the Br minus here does not attack the positive charge yet, right? Because we have to draw in the resonance structure and see what our temperature is to see what product we want. Right. So the resonance structure like that. And then I'm only drawing one because this is symmetrical. So this carbocation is secondary allylic. This carbocation is tertiary allylic. This alkene on the first one is tri-substituted. The alkene on the right is di-substituted. So that means that this is our thermodynamic product, more stable alkene. This is our kinetic product, more stable carbocation intermediate, right? So then the Br minus attacks to get whatever product we want, depending on the temperature, right? So the thermodynamic product would look like this. And I'm gonna draw these bonds, or actually not, let's do it Levin's way. She'll want it like this, that, and then you could do bromine right there as a flat bond, right? Because this carbocation is flat and planar. So when the Br minus attacks that carbocation, it could attack either on the top side, giving you a wedge product, or the bottom side, giving you a dash product, right? So we could also see that this could have been a dash, that could have been a wedge. So I'm just gonna make it flat, make everything flat here, right? It's not gonna be racemic though. You can't say racemic. So you can just put it like that. That's the thermodynamic product. Our kinetic product would be this. Okay. So that's the symmetrical conjugated diene reaction with X2 halogenation, right? Let's do the other two and then move on to diels-alder really quick. Okay. So it's asymmetrical. We have to react with 2 of the alkenes. Boom, boom, kick out the chlorine, and we're gonna get this chloronium ion here. Right? Now, this next step is gonna leave by itself. This one here is gonna have the more stable carbocation rather than this one because it is allylic, right? The bond where it breaks is gonna be the bond between the chlorine, the halogen and the allylic carbon. So it's gonna break off like that, right? In order to form the more stable carbocation intermediate here, right? And then I'm just gonna leave this as a flat line chlorine because this could have been a wedge or dash, right? I just chose it to be a wedge, but this could have been a dash as well. Now I do resonance to get this resonance structure here. Okay, so that's one of the resonance set. We can't go from here, right? Because there is another alkene to react with, and it's gonna give it a different set of resonance structures because this is asymmetrical. So to show that, it's gonna look like that. It's gonna give us CO plus, do the same thing, kick it up this way at the allylic carbon to get this resonance structure. Okay, so now let's compare which resonance structure we are going to keep. Right, that was just the first one. That's that. Okay, that's not resonance arrow. That's going to be there. Actually, it's going to be up here. Boom. Boom. Yeah, there you go. That's the resonance set. The other one. Okay, so this is a tertiary allylic carbocation. This is a secondary allylic carbocation. This is a secondary allylic carbocation, and this is a secondary allylic carbocation. Right, we're gonna get rid of the top one because they have worse resonance structures. This one has better resonance structures, so we're gonna keep that one. Now let's look at the double bond. The double bond on the left is di substituted. The double bond on the right is tri substituted. So that would make this the thermo intermediate. This would make it the kinetic intermediate, right? And then to finish up everything, the CO minus comes around to attack the carbocation to get our final products here. CO, CO, boom, 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 right. So this is our kinetic product. Check that. Oh, wait, drew in the wrong thing. I drew in this one. Okay. The chlorine attacks here, so the chlorine has to be there. The bond is still there, stays there. Right. So this is our kinetic product. That's right. This is our thermo. That's right. Okay. So that's how you can do that. Hydrohalogenation and halogenation reaction, right? So in the reaction mechanism, would we show the forming of chloronium ring because Maria said not to form the epoxide-like ring and just leave it as a carbocation. Yep. Maria is right. Like you want to draw the carbocation here, right? But to better visualize where the carbocation comes from, I like drawing out the chloronium or bromonium ion ring, epoxide-like ring first to connect the previous material that you learned into this new material, right? Because this would happen first. And then before the Br minus or Cl minus attacks the more subside, kicking out the ring, the difference in this step here for this reaction, because it's conjugated, is that we want to form the allylic carbocation. So this ring here is not going to exist very long. It's going to break off right away to form the more stable carbocation, right? So since it doesn't exist very long, there's no time for the chlorine minus ion to attack that ring, right? So this right here does exist, does get formed for a brief amount of time, but we want to kick out the leaving group like an SN1 reaction for this type of reaction, right? And then we do the whole resonance structure, right? Yeah. And for leavings and let's say Nasseri helix, they include this ring for sure in the mechanism, right? I have to check Leaven's notes to see if she also includes this in the mechanism, right? Yeah, no problem. But always stick with the professor's way of doing things to get the points, right? So I'll have to check what Leaven's does for this, but this does happen in the intermediate, yeah, right? Like conceptually, that would happen. That's how that carbocation gets there. Because if you just go straight into this point here, it's confusing on where the carbocation came from, right? It came from this ring, epoxide-like ring there. Okay. So I think does that make sense? Do you guys want to go over diels-alder now, and then the chapter 20, I mean number 20 synthesis, and then NBS NCS? Let's see. Let's do diels-alder. Yeah. Yeah. Okay. Okay, let's do 2 of these. And then go over the other problems. Here's the hardest one. Okay, which ones would you guys like to do? A, B, C, D, E, F, or G? Let's do 2. Let's do 2 of these. And then go on to the next. Z? Z, oh my god. That's Leaven's vocab section right there. A, B, C, D, E, F, G. All the way to Z.
Am I still able to learn even though I'm not doing this?
I think, wait, what was that? Sorry?
Am I able to learn even though I'm not participating in this? Really?
Um, yeah, you can join. Yeah. Uh-huh. Right. Like
Alright,
you
alright.
can listen in and participate or learn if you want.
Yeah,
Yeah,
yeah.
because like you haven't taken the prereqs for this class yet, Gen Chem, but like this could like show you what's ahead coming up. You
Yeah.
know.
So,
Yeah. Yeah, it's okay. Yeah. So let's do C and then
and
another
then
difficult one.
and then you can do A perhaps.
A. Yeah. A is pretty hard too because of that ring. So let's do A
Yeah.
and C. Yeah. Okay.
Alright,
Let's do A
alright.
and C. Yeah. Let's do it. Okay. So before we go over that, let's go over the endo rule. So this is a basic diene. This is a basic dienophile, right? Dienophile. So this is the pocket between the diene and dienophile that's going to be formed, right? Think about the bond that are going to be formed here. These are the new bonds that are going to be formed between those 2 carbons, right? So, and that's the pocket right there, the pocket of the reaction. Now let's look at out groups and in groups. On the diene, right? Out groups and in groups, they only refer to the groups on diene. Out and in groups refer only to carbons 1 and 4, right? These are arbitrary numbers. Carbons 1 and 4 are going to be here. 1, 2, 3, 4, 5, 6. Right. So 1 and 4 here, they're going to be the carbons holding the out or in groups, right? So if you see a group on carbons 2, 3, 5, or 6, you can't say those groups are out or in groups, right? Out or in groups will only be on carbons 1 and 4. So if you see a group that is going outside of the pocket, on carbons 1 or 4, those are considered out groups. If you see a group going inside of the pocket, then these are considered in groups, right? And then the dienophile will usually go with EWGs, electron withdrawing groups, and then the dienes will usually be like EDGs, electron donating groups. And then whatever groups on carbons 2 or 3, they will always stay flat and planar, right? There's no wedge or dash there because that's sp2, and it will stay sp2 in the product, right? Because the mechanism arrows are something like this, reacting with heat, where this is atom 1, 2, 3, 4, 5, and 6, right? Where the new bond between 1 and 6 came from that double bond right here. New bond between 4 and 5 came from the double bond right here on the dienophile. This double bond between 2 and 3 came from the double bond between 3 and 4, right? So that's all there is for the mechanism arrows, right? The mechanism for diels-alder, very easy, right? Just 3 arrows simultaneously. What makes diels-alder hard is the regioselectivity of this and stereoselectivity of this and the endo row, right? Because the regioselectivity of it, if there's 2 groups on the dienophile like that are cis, those groups will have to stay cis. If 2 groups are trans, then those 2 groups would have to stay trans, right? And then the other thing about stereoselectivity is the endo row here, right? Well, the endo row is saying that the out groups on carbons 1 or 4 will be cis to the EWG electron withdrawing groups, to the EWG on the dienophile. Okay, so let's do a problem to see what that means, right? We see that this is, so there is another thing about regioselectivity as well with the charges aligning, but we'll get to that problem if there is a problem on that. Let's see if there is. C, so C doesn't have that. Let's see, boom, boom, boom. Charge. B does have that. Okay, let's actually do 3. Let's do A, C, and what's another hard one here? A, C, and D. A, C, and D, because it's not oriented correctly in that right. Our diene backbone. This is our diene backbone, right? And then determine bridge between carbons 1 and 4. Let's work 1, 2, 3. Is it in group, right? Because it's inside of the Oh shoot. Okay. Let's see. Okay, let me just re-explain that. Right. So look at the very first atom attached to the system, either the diene or dienophile, to determine if it's an EDG, right? If the atom is partial negative or negative charge, it's an EDG. If the atom is partial positive or positive charge, it's an EWG, right? Another thing that you can see as well for EDG is that if you see any R group, like methyl ethyl isopropyl, that's an EDG. For EWG, you could also see a halogen X, like chlorine, bromine, or iodine, right? So looking at this dienophile here, the very first atom attached to the dienophile is partial positive charge, right? That makes that the EWG. It's going to withdraw electrons. And so when we draw in the product, like do that, we get this cyclohexene base product right there, right? And let's keep track of our atoms. 1, 2, 3, 4, 5, 6. 1 and 4 had a CH2 in between them, right? That CH2 is going to be right here. I'm going to draw as a wedge right there and a wedge right here. Right, to make it more clear, let's highlight it purple. This purple bridge right here is this purple bridge right here, right? The wedge is showing that those bonds are going towards you. So there is like a hole in the ring right here, right? There's a hole going through that ring. This is a bicyclic ring. It's easier to show it in a different conformation, which is the way Leibniz draws it. I'll show you that after we finish up this product, right? And because this is an in group right here, this in group is trans to EWG based on the endo rule, right? So since this is a wedge, the EWGs would have to be a dash. Right, so that's the final product, and we can say racemic, right? But to make this bicyclic ring more clear, we could redraw it in this form here, right? Where this is atoms 1, 2, 3, 4, 5, 6. And then that purple ring right there that I highlighted is this purple ring right here, right? Between 1 and 4, that CH2 between them. Bicyclic ring. There's 2 cycles in this structure, in that ring, right? 2 rings in the structure. So 5 and 6, since this is going up, this group here has to go down. Like that, right? Final answer. And we're seeing it. Okay. The name of this new compound, I'm not too sure. I'm not too sure what the name of this would be. Yeah, I'm not too sure what the name of this is. Yeah. Okay. Let's do C. Okay, so first I highlight my diene and dienophile backbone. This is my diene. This is going to be my dienophile, right? But the dienophile there has an extra bond, the triple bond. And another thing, right, is that when we do these diels-alder reactions, we're used to seeing it in this kind of orientation format, right? The dienophile is good. The dienophile is kind of weird. So we got to rotate that to make it more clear, right? So keep that the same. Rotate this dienophile like this. And this is transition. It doesn't matter anyway because now this is going to be 1, 2, 3, 4, 5, 6. Right. Draw the pocket between the diene and dienophile to determine your in and out groups on carbons 1 and 4, right? So now let's draw in that pocket in between the diene and dienophile, like that, right? So 1 and 4, there's no out group, right? Because there's nothing coming out of the pocket right there, so no out groups. But there is an in group, which is that in group right there. So that means that this group has to be trans to these EWGs. These are EWGs because the very first atom directly attached to the system, which is this carbonyl carbon here, right, is partial positive charge, making them EWGs, electron withdrawing groups. Okay. Reaction arrows. 1, 2, 3, 4, 5, 6. Between 1 and 4, there's a CH2, which is this CH2 ring, which is going to be trans to whatever this is. But we used one of the bonds of the triple bond to make this new bond, right? So that means that between 5 and 6, there's still a double bond right there, right? There's still an unsaturation between 5 and 6 because we just used one of the bonds of the triple bond to make a new bond between 4 and 5, right? That new bond right there that was formed between 4 and 5 came from only one bond of the triple bond, making 5 and 6 now a double bond, right? So now the stereochemistry on 5 and 6 does not matter because it's going to be flat and planar since it's on an sp2 carbon. These are sp2 carbons here, right? If that wasn't an sp2 carbon, then the stereochemistry of it would be a dash in order for the in group to be trans to the EWG. But in this case, it doesn't matter because we have sp2 carbons there, right? Okay, let's do one more here, and then do NBS, NCS, and then the synthesis column at the end. Right? This is going to be D. Okay, now this one here is harder than the previous two because the previous two, we didn't have to worry about regioselectivity. We didn't have to worry about charges at all, right? So for this one here, this is our diene backbone. This is our dienophile backbone. Let's redraw this in the format that we're used to seeing it in, like this. Boom, boom, boom. And like that. Okay, so when you see an outgroup like that, right? Imagine this was some kind of oxygen with pairs of electrons. When we draw resonance structure here, there's going to be a negative charge on that carbon, right? If there's an EDG here and we do resonance like that, there's also a negative charge over there, right? So imagine that there's a negative charge here, right? Now this is an EWG, the NO2, because the nitrogen has a full positive charge, right? So it's going to withdraw electrons from that dienophile, making the positive charge on the dienophile down here, right? So when you do resonance, you'll see where the charges are. When we look at these charges right here, we see that in this form here, in this orientation, the charges do not align, right? Because if we look at the pocket, we want them to be on the same spot, right? This negative charge is on the opposite side as that positive charge right there. So that's a problem. We have to flip something. And I like flipping the dienophile because it's smaller and it's easy to flip and draw. So the way I flipped it, there's now going to be a positive charge here and a negative charge there. Now the charges are aligned and we can proceed with the reaction, right? This is probably one of the hardest concepts of diels-alder, where they could trick you by drawing it in the wrong orientation, a different orientation, where you have to rotate it into a way that aligns the opposite charges like that, right? In order for the reaction to go through. The other hardest part about this is the endo rule. The outgroup has to be cis to the EWG, right? So now once we have our charges aligned, everything is going to be normal now, right? It's going to be that. And I went more in detail with that, like charges aligning thing in the last office hours. But right now, we don't have that much time to go over that. To do this. So once we do those arrows, we're going to get this here, right? Where this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right. Notice how the methyl group on carbon 2 stays flat and planar because it stays on the sp2 carbon, which is that sp2 carbon right there. Right. If you look at the pocket between the diene and dienophile, we do have an out group, right? That methyl group there is an out group because it's outside of the pocket between the diene and that dienophile, right? And we already said that this NO2 is an EWG. So this methyl group here and that NO2 group are going to be cis with each other in the reaction, right? So let's make it a dash because that's how like these products are usually in dashes. You can make it a wedge as well, but I'm going to stick with the convention. If that out group methyl is a dash, this NO2 group would also have to be a dash, right? And racemic. They both could have been wedges as well, right? And then to draw in Levin's way, Levin's convention, she does it like this. Boom, boom. And then this is 1, 2, 3, 4, 5, 6. 4 methyl group going down, down. I don't know how's it down like that. Yeah, down. And then 5 NO2 down as well. Right. Both of them are cis, down, 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 down. The out group is cis to the EWG, aka endo. Right. And I can explain why that's the case in the next office hours, and also why the endo will give you the exothermic product, whereas the I mean, not exothermic. What am I talking about? The kinetic product, kinetic product, and then the exo product would give you the thermodynamic product. Yeah, there you go. And this would be most likely on the vocab section for the next midterm. This endo exo stuff with the thermodynamic kinetic stuff, right? But that's important. The endo product gives the kinetic product. The exo product is the thermodynamic product. Okay. So that's diels-alder. NBS, NCS, right? Let's say we have this diene here that's asymmetrical, reacting with NBS and light. When you see NBS or NCS, think of allylic halogenation, right? Bromination if you have NBS, chlorination if you have NCS. Right, so this is not going to be conjugated. Let's make it alkyne. That. And we have that. And then no. Okay, this one here. Right. So the first step to predict the product here is first locate your allylic carbons. That's an allylic carbon there. That's another allylic carbon there. One carbon away from the alkene. Then figure out which allylic carbon would have the most stable radical. The most stable radical is going to be on that right one there because it's more substituted, right? So the intermediate is going to look like this, where the radical is going to be on the more substituted carbon like that, right? Where this can do resonance like this. We draw single hook arrows to show the movement of one electron. This one electron radical here is going to form a double bond with one of the electrons of that double bond, right? Because that bond here has 2 electrons. The other electron is going to go to make a radical on that carbon right there that it's on, giving us this resonance structure here, right? And then the products would be putting a bromine if you have NBS on the radical, or chlorine on the radical if you had NCS. Right, so NCS is just NBS, but adding chlorine instead of bromine. Right, where this would be your major product, this would be your minor product, because we have a tri-substituted alkene here, and we have a di-sub alkene here. But for predicted product reactions, I would include both products to get full credit. Include both products for NBS and CS, right? But the first thing here is locate most sub-allylic carbon and ignore the other allylic carbon, right? We just ignored this allylic carbon entirely, which is why we didn't mess with the other resonance set. We just worked with the resonance set that came from the more stable allylic carbon, right? More substituted allylic carbon in the first place, right? Okay. Let's finish off this office hours with number 20 on the problem set. Let's see. Let's do this. Number 20. Let's see.
Actually, can you do 21?
Number 21? Yeah, let's do 21.
Thank you.
Yeah. Okay. Paste. Okay. So let's try the synthesis problem without looking at the answer choices and match up the steps with the answer choices, right? So we have H, boom, 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 H terminal alkyne turning into this aldehyde here. Boom, boom. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Wait, is that right? 1, 2, 3, 4, 5. 5 carbons. 1, 2, 3, 4, 5. Yeah. Okay, so I'm gonna label this 1, 2 carbon to show that that 1, 2 carbon is that 1, 2 carbon right there. So this yellow highlighted chain right there is this yellow highlighted chain right there, part of that product, right? In the products, I see that we have an aldehyde at the terminal end. So thinking of my alkyne reactions, I'm gonna think that this came from hydroboration oxidation from my terminal alkyne, right? So the first step is that. Second step is H2O2, NaOH, water, because when I see an aldehyde at the end, I think of hydroboration oxidation of a terminal alkyne. So that's 5 carbons. So that's 1, 2, 3, 4, 5. Right. 1, 2, 3, 4, 5. Where the 1, 2 chain there is this 1, 2 chain here. Right. Now, the difference between this intermediate and this reactant molecule is that this intermediate has an R group, that propyl group. We can make this carbon here nucleophilic, and this would be the electrophile by deprotonating that carbon 2 with NaNH2, strong base. Right, NH2 minus grabs the H minus. That bond breaks up and goes onto the carbon 2 to get a negative charge there. Right, this is our alkynyl anion nucleophile. Right, and now to get to this point here, we would have to bring something that would add that new R group onto the negative charge. Right, and to make this carbon here electrophilic, positive charge, we have to give it some an electronegative atom like bromine here. 1, 2, 3, 1, 2, 3, right? In order for us to have this star attack this dot and kick out the leaving group for this SN2 reaction here to get that terminal alkyne, right? And then hydroboration oxidation would give us this alcohol on the last sub side, the Markovnikov side. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? Because hydroboration oxidation is an antimark reaction, which adds alcohol on the less subcarbon. But we don't stop there because we have an enol intermediate, right? Which would tautomerize into the carbonyl form, where the carbonyl is going to be on the carbon that's attached to the alcohol, right? So that carbon there is that carbon right there. 1, 2. Okay, now let's look at the answer choices. First, we add reagent NaNH2, where is that? S to form the alkynyl, right? Anion, then add reagent CH3, CH2, CH2Br. Hello. Oh, Z right here. Z. There it is. Z to act as an electrophile SN2 mechanism. Then we add reagent. This is hydroboration oxidation, 2 steps. Hello. Where is this? J, followed by reagent hydrogen peroxide, L, to give the product with anti-Markovnikov regional activity. The initial product of this reaction contains an enol functional group, which rearranges to the final product via a tautomerization mechanism. It's either tautomerization or keto-enol tautomerization, but I think tautomerization would work. Should accept that, I think. If instead we wanted to form 2-pentanone, we'd use the reagent. So instead of that and of this here, we wanted to form this reaction product. 1, 2, 3, 4, 2-pentanone. Right. We see that the carbonyl is at the Markovnikov position now, the more substituted carbon. So instead of hydroboration oxidation, we are going to do mercuric ion catalyzed hydration with HgSO4, H2O, H2SO4. Right. Think of it as the oxymercuration demercuration version of it, where it adds the alcohol in the more subcarbon, right? But then we still have the enol intermediate, which will eventually tautomerize into the 2-pentanone, right? We would use reagent H in the last step to add the oxygen with Markovnikov regional activity. Yeah. Be careful of this right here, alkynyl anion. Is that what Levens calls it as well? This this negative charge on the alkyne there. Does she call that alkynyl anion as well? Or like, what does she call it? Because like there's different names for the same thing, unfortunately. Alkynyl anion. Any questions on this problem? Did this make sense?
It's fine. Also, it's
Okay.
like 10.
Yeah. Uh-huh.
Yeah.
Okay. Yeah. So hopefully that helped, Jane. Yeah. Did you have any questions about that, Jane?
No. Thank you so much.
Yeah, no problem, Jane. Was that the last problem of the problem set, problem 21?
I think so.
Okay, that's good. No NMR on this problem set?
Okay.
Oh, there's no NMR. That's all good. Okay. Yep. I'll see you in our next session, Jane, or tomorrow's office hours.
Thank you.
No problem. Hey Ryan, hey Davi.
Long day.
Hey there, hey
Yeah,
there.
long day. I woke up at
Yeah.
4:30 a.m. and then I
Jeez.
went to work out with the club, and then I went home. I went to study at the library until 8 p.m. and then I went home, ate dinner, and then office hours. So long day.
Wait, what time did you wake up?
4:30 a.m.
Oh. Did you take a nap or?
Yeah, I did after school.
Okay.
Yeah. Davi, it's 2 a.m. over there. 2:10.
Yeah.
Go ahead.
Also, do you know any tools for calculating reactions, like any free ones?
Oh, like practicing reactions.
Like to calculate a reaction for fun, you know, just for fun.
Oh, like Gen Chem or OChem.
Like any, and
Yes.
that works.
Yeah. So since you haven't taken Gen Chem yet, use this website to learn AP Chem, and then we could talk about it soon when there's no
Okay,
one
so
going up.
All right.
Okay, and Ryan's gonna take this class too, so then you and Ryan can work on it together too, and then we can go over it together as well.
Yeah, right.
Uh-huh. Yeah. Dang. I need a
damn,
little break.
that's tough.
Mhm.
Like, how long was your nap?
I after school I napped for like an hour, and then I had to go study because I have 2 exams tomorrow, so I have to study for that because yeah, I need to pass those classes.
God damn.
Mhm.
Yeah, it's like, wait, you had office hours yesterday?
Yeah, I did last night too.
Ew.
Mhm. Mm. You guys want to do what 17 push-ups?
Oh wait, yeah, it's about around that time. Yeah, wait, let me check.
Yeah, let's do 17 push-ups together.
I don't.
literally,
I don't want to do that.
Are you in bed right now, Davi?
No, but now I'm better, and I'm just sitting on my set right now.
Oh shoot. Okay. Want to do 17 push-ups, Ryan?
okay.
Okay, let's do it. Let's do it. Davi, count for us. Count to 17.
Okay.
I don't.
Okay.
2, 3,
1, 2,
4,
3,
5,
4, 5,
6,
6,
7,
7,
8,
8, 9,
9,
10,
10,
11,
11,
12, 13,
12,
14,
13, 14,
15,
15,
16,
16, 17.
17. Ah. That was good. I feel the pump.
Whenever I get to my attention span's kind of low sometimes, so what I do is I just set a timer for 10 minutes, and every 10 minutes goes by, I just do 20 push-ups.
That's good. Like it re-energizes you too, right? Like do you feel like more energy
Blood
afterwards
pressure,
too?
yeah,
Yeah. Yeah.
yeah.
Oh, free tools to calculate chemical reactions. Oh, like what do you mean by calculate chemical reactions?
Like to that automatically calculate chemical reactions for you, like to just because I want to see chemical reaction stuff, you know, that automatically calculate for you, you know.
Like give you reactions to practice with?
What?
Like give you chemical reactions to practice with? Like to practice chemistry?
Well, it sometimes to practice, sometimes to just use for fun, you know, both basically.
Hmm.
Yeah. I don't know any website. Do you know any website, Ryan?
I've literally been busy with school. I wrote like an entire essay in one sitting, but like it's a rough draft, so it's like
Yeah.
yeah.
Yeah. Did you check out
Yeah,
the website I sent you earlier, Davi? The apchem.org one? Did you check out that website?
yeah, check it out. I watched the guides after the session.
Okay. Oh yeah, let me also send you the Khan Academy one as well. Khan Academy chemistry.
All right.
Yeah. How's school been going so far?
Been going alright, to be honest.
Oh yeah, it's like the 10th day of school because
Yeah,
school started. Wait, no. Yeah, school. Yeah, it is. This 10th day of
yeah,
school.
yeah.
Okay,
Two.
so actually use this link, Davi. This is high school chemistry, right? Because yeah, you're still in middle school, so I recommend just starting there, learning, watching the videos for high school chemistry, doing the practice
Alright,
questions
got
there,
it.
watching the videos, and then learning from there as well.
Alright.
Right. And then once you finish that, once you finish high school chemistry, you could move on to AP chemistry. AP chemistry.
All right,
College
got it.
chemistry. College chemistry, yeah. And then once you finish like general chemistry, you can move on to organic chemistry, which is the class I mainly do there. I mainly
All
do
right.
chemistry.
Yeah.
yeah.
I'll go learn it now, I guess.
yeah.
Yeah.
That's good. Dang.
Mm.
What AP classes are you taking again, Ryan, this semester?
This semester, AP Lang. Well, I have a microbiology honors class, and then
Mm.
AP Lang, and then AP Chem. That's it.
Mm,
Oh yeah,
right.
I'm taking pre-calc, and then next
Uh-huh.
semester.
Yeah. And
The
you're
the
taking AP
the
Chem next semester? Like you're starting that next semester?
yeah. The funny thing is that I also have biotechnology, and it's like physics. They're teaching, so I have like a pre-calc, AP Chem, and then physics, biotech, physics, and dance.
Uh-huh.
Mm.
Dance? Oh, you're taking dance class too?
Just because I didn't want to like kill myself.
Uh-huh.
Yeah.
Dang. Yeah, that's good. That's smart.
Mm-hmm. Honestly, everyone looks so tired. It's like the 10th day of school. It's like, damn, it's already that time.
Like everyone in your school is so tired already.
Yep. I mean,
Dang.
no, everybody in biotech, not like everyone else is fine. We only
Yeah, that
represent like 8%, but I'm surrounded by like those 8% of people who are in the same academy as me.
right. That's how it is, you know?
Yeah.
Yes, how it is. Wait, what day of school is it for you, Davi? Like did you just start school this week or last week?
Yeah, last week, basically.
Oh, last week. Okay.
Yeah.
Mm. Last week. I don't think I went to your meetings last week either.
Yeah, you guys were busy, right? With school and homework and everything, adjusting into school.
Yeah,
Yeah.
yeah, yeah.
Yeah. Dang.
I'm kind of
And,
tired of it.
and since I do your workouts at like 1 a.m., I need to have almost free time as I want to participate in your work office hours, you know.
Mm-hmm.
Workout.
Yeah, I literally have a lot of free time at 1 a.m., you know, when my
Wait,
parents are
A
sleeping.
don't
lot.
you have school tomorrow? Oh,
Yeah,
or
I
is
do.
it?
Yeah, I
Oh,
do.
you do have school. So what time?
It starts at let me I don't know the name of it. I don't know how to explain it I also type in SATA, right?
Okay, okay.
I'm doing my Spanish homework right now.
Spanish homework. Yeah. I'm about to study for my two exams. I
Mm.
have tomorrow. Continue
Tomorrow.
studying.
What time? Like morning, evening?
Yeah, it starts at 8 a.m. The
Jesus.
second one starts at 9:50 a.m.
Damn.
I know. Wish me luck. I'm gonna need it.
That's like, hmm.
Oh, 1 p.m. Oh, your school starts 1 p.m. That's
Yeah,
dang.
yeah, it is. Mhm.
Oh my god.
Wow. What time do you get back from school?
I like 6 p.m. That when I get back to school. So basically 5 hours school, 5 hours.
Not bad. You get to eat lunch. I don't even eat like breakfast or lunch. I just eat dinner, and I just eat a whole lot of dinner.
Rape. As how good are you at chemistry, Ryan? How good are you at it?
17?
No, not your age. Like, how good are you at chemistry? How good are you?
Oh, how good are you at chemistry?
Yeah, that.
Mm, I can do molar mass calculations, but besides that, it's just like a lot of math instead of chemistry.
Yeah.
Mm. It's like
I mean, I can do basic chemical equations. As predict the most simple structures, like chemical structure. I can predict really simple ones.
mm. Mm. Yep. Brian.
Yeah.
I feel bad for some of my other friends because some people have AP psychology, the microbiology honors, and like where it just has a bunch of research and labs, and then some people like have AP physics in the same thing. I'm like, oh, three
Oh my god.
APs. Huh? Yeah.
Are they dying?
No, they're not. They are hella smart. It's just like they just decided to carry all that.
Oh my god, dang. They're trying to get into like a really good college, really good school, huh?
Mm,
That's
yeah.
good. Yeah. Dang.
I mean, for me, I promised myself that I would never go to sleep later than 1 o'clock
Uh-huh. Dang.
because I've taken a time lapse of me just pulling an all-nighter, and it's like, oh man, I hate this. And then I also took a picture of myself. I was like, God damn, I look so depressed. And then I remember one day I just did an all-nighter, and then I did another all-nighter right after that, and then I just could not go to school the other day. I just slept the whole day. It's like, oh shoot, yeah, yep. It's pretty bad, but last year, but like this year, I just never again. I don't really care if I don't do as well, but in terms of college, but I know that I always have a safety school called Sac State.
Uh-huh. Sac State.
Yeah,
Yeah, like the CSU, right? Like there's also
yeah. It's just
San Jose State.
I can't sleep later than 1 or 2 o'clock, and that's my boundary.
1 or 2 a.m. Yeah.
Yeah.
Right.
Besides, my time management skills are good, but I miss losing an hour just by scrolling on my social medias just to see what's up, all my just because I need Instagram to use for all my clubs and stuff.
Right. Dang.
I only use like Discord for my social media. That's the only social media I use, to be honest.
You don't use social media, you only use Discord?
Yeah, only Discord. That's the
Oh,
only social media I use.
yeah. No Instagram, no Facebook, no Snapchat.
No, none of these dots. Only
Yeah.
Discord.
Ryan would advise you to not start those, huh?
Uh, uh, at your own risk.
At your own risk. Yeah. Like
Hmm.
if you do start it, like try not to get addicted to them.
I
Yeah,
mean,
you want to be
I started before, but it just felt really boring and
actually
addictive.
instead of doing scrolling using social media, just use Khan Academy for chemistry and OChem when you AP Chem when you have
Yeah,
time.
yeah. Like
Alright,
first,
alright, alright.
um, do Gen Chem and then AP or College Chem and then organic chemistry and then we could work with you on that together here, right? Like and then
Alright.
yeah, like when you
Yeah.
work through the problems.
Mm. Also, there's club rushes tomorrow.
Ooh, Club Rush.
Yeah.
Yeah. What clubs are you in right now or interested in?
Um. So basically, last year it's just I wasn't really a part of any clubs because I focused way too much on academics, but it kind of just hindered any kind of socializing from where I was, what I was doing, because I just
Uh-huh.
went home, studied, and then that's it. It's I go to sleep. It's hella late. It's oh shoot, I should really focus on having fun because even if I don't get into my college, I still want to have fun in high school before it ends.
Right. Before it ends, that's good. That's good that you're thinking about that. Make memories. Make as much memories
Hmm.
as you can. Are you planning to join a sports team in high
Um,
school?
in tennis is in the spring, not the fall.
Mm,
So yeah,
yeah. You could do
and then
conditioning, like run, build up your endurance, cardio,
yeah, I think my
entry.
endurance is really good and my strength is really good. It's just practicing. But
Uh-huh.
also besides that, let's see. I'm gonna go to like like lion dance club. Like I want to perform like on like in this and there's like this gym and like you perform like this kind of thing where I forgot what's it called, but like it's just like main multicultural event. Yeah, it's like that's what it's called. Yeah.
Uh-huh. Right. Multicultural event. Right. Like the performances, right? Like the shows and everything.
Yeah, and everything.
Yeah.
Yeah.
Yeah. It's crazy. Davi, do you do any sports?
Nope, I don't. I
No.
used to do swimming, but since COVID, I just stopped it, to be
Mm.
honest.
Mm.
I had to forcefully stop it because of the COVID pandemic.
Oh, the
Mm-hmm.
pandemic.
Yeah, they forced it to stop the swimming class, and once the classes came back, my parents didn't buy them anymore because they were too expensive for them.
Too expensive.
Yeah.
Mm. The reason why I didn't want to like join any academic clubs was just because like when I joined like the freaking Sayali Discord, they were all talking about like how like late their sleep schedules was, how many APs they had, and like it was like, oh, I had 14 APs. It's like they still couldn't get into like their dream school. It's like what the hell?
Yeah. So competitive. Yeah.
Yeah,
Are there APs in Brazil?
What?
Do you have advanced placement classes or college board AP classes in Brazil? Or well, actually, I don't think you know about that yet because you're still in middle school, right? Like not high school yet.
true.
Yeah, I'm in middle
Yeah.
school right now, so I don't know that stuff yet.
Right. Yeah. Dang.
Mm. How long you
Did you guys
gonna
meet new friends when you
What?
guys did you guys meet new friends when you guys back to school, or did you guys stick with the old
new
friends from
friend?
last year?
Actually, basically, like throughout kindergarten, I always had like the same people in my classroom, and like it's just like I've never talked to them at all,
Mm-hmm.
or but and like now it's just like they're all in my classes, and like I get along with them because I'm like getting really good at being academic, and like I can actually know what I'm talking about when I'm talking about like the subject. Is like, Ryan, help us. It's like, yeah, they need my help. I was like, yes, let's go.
Yeah, that's good. Yeah, like when you're able to help people, giving them the aha moment, it feels good. It feels fulfilling.
Yeah, and like making more connections.
Mm-hmm.
Yeah.
Right. Making more connections as well. Yeah, you get a lot of connections when you're able to help a lot of people.
Hmm.
Yeah. Yeah.
Hmm. How did you get your community service hours, by the way? Since like I probably need to. Yeah.
Oh, so there are some clubs that does community service. I joined Interact, but there's also Key Club or UNICEF.
Yep.
Uh, I also volunteered at this Vietnamese community organization at the public library nearby for community service hours. I
Hmm.
also contacted hospice centers to volunteer, donate, help them with the front office, front desk stuff. Um, yeah, that's all I did. Like the club, reaching out to like hospitals, hospices, and Vietnamese or like other communities like libraries, public libraries to volunteer and help out for
That's
those
really good.
hours. Yeah.
It's like I feel like school is like becoming more and more easy because I'm enjoying learning more and more. So like it's kind of like more of like not my main focus, but it's like I can do it with stuff on the side. Like I
Uh-huh.
can work out and also do school.
Oh
So
yeah.
like I could also use the time I work out to like volunteer or do
Uh-huh.
something else.
Right. Yeah, that's good because like you save yourself for not taking a lot of AP classes that would steal a lot of your time. That will
7 hours,
reduce your
7
extracurricular
APs.
time. Yeah.
Yeah.
Dang.
Hmm. I did save myself in my classes. I don't know, writing is kind of time consuming. but it's fine because I like writing. I force myself to like it. Right after I actually, like, during the summer, I just like I quit video games. I deleted all my socials. What am I supposed to do? Oh, there's a book and there's a pen, and just reading and writing, and then that's it.
Dang.
But now it's like I don't know what my hobbies are just because like I don't get to do them every day. It's like
Mm.
I delete my socials sometimes, so it's like, what do I do?
What do
Oh,
you do? Yeah. There's something.
I just needed like ideas for like volunteering and stuff, but that's good that you like gave me them.
Yeah, like ideas on where to find them, but what to look for.
I was like, I should look through my LinkedIn again.
Yeah.
How long you gonna stay up?
Probably
What?
like, yeah, really late. How long are you staying up, Davi? Like, it's so late for you right now.
Oh,
Yeah,
almost
it's
3
like
o'clock.
it's like 2 a.m. for me right now, and I'm
2:30 a.m.
still not feeling sleepy. Still, I'm
Yeah.
still
You are lucky that you go to school at 1 p.m.
yeah. Don't know why I'm not feeling sleepy yet. I don't know why.
You're not sleepy.
Yeah.
Dang. What time do you usually sleep? Like, what's your usual sleep schedule? Like, what time do you usually sleep, and what time do you usually wake up?
What?
What time do you sleep, and what time do you wake up?
I usually sleep at like 10 p.m., but I'm staying up till 2 a.m. right now.
Oh shoot! Dang. It's crazy. Okay. I'll let you guys go do whatever you guys need to finish tonight. Sleep early if you can, and then wake up early. To maintain a good sleep schedule. I'm gonna stay up a little bit to study for tests tomorrow. But it was
All
nice talking
right,
to you
all right,
guys.
all
Yeah.
right.
2 tests.
2 tests. I know. I'm kind of stressed right now. Oh, wish me luck. I need the good luck. Wish me good luck.
Yeah, good
All
luck.
right, good luck,
Thank
good
you.
luck
Do
for
Thank
like
you.
you.
do a push-up
Bye.
before you leave your house.
Yes.
Yeah.
I need you guys to just good luck. Oh my gosh.
Good luck.
Yeah.
Thank you. Yeah. Okay. Good night, guys.
Good
Good
night.
night.
Night. Bye.
Good luck. Good luck.
Thank you.
Yeah.